I'm just going to hit record. Thank you for joining me. I started with a bit of warm-up music. I asked everybody, is the warm-up music okay? 31 people said yes, 2 people said no, and no response from 20 people. So if you like it, I'll keep doing it. Yes, Jazz, absolutely, Abdul Rahman. I'm happy to take your requests for warm-up music. So if you have any, put them in the chat box. Okay, love jazz. All right. Hope you're having a good day. This is the tutorial for like a balanced experience. So I'll be doing some, sort of medium difficulty questions. But I'm happy to hear your questions. So what I suggest we do is I'll just start off with some problems and we can solve them together. But I'm happy if you want to talk about specific things or specific questions, or if you don't, if you want some extra information about something. Today's tutorial is mostly going to be about algebra, okay? So I thought we could work through some algebra problems and see how we go. All right, so let me share my screen. So you can see here that, that these are some questions from the algebra booklet. And some of the suggested problems involve, 16 and 21 and a few others. So I thought what we could do is work through these problems together. If I make a mistake or if something's not clear, just let me know either in the chat or you can get on your microphone and let me know how things are going. So yeah, Omar, the pinching theorem, good question. The pinching theorem will come on in Thursday's lecture. Okay, so one of the difficult things with the tutorials and the lectures is the tutorials start the same week as lecture 1. So sometimes it's a little bit mismatched, but you can think of it as preparation for the lecture. So that's how I think of it anyway. Yeah. So you'll see the pinching theorem in my lecture on Thursday. All right. Yeah, same thing. Practicant, the squeezing theorem and the pinching theorem are the same. So let's have a look at one of question 16. Okay, so you've got 4 points and you're asked to see if the vectors A, B, and C, D are parallel. Okay, and are there any parallelograms here? So these are not difficult. Pratikanch, how do you say it? Oh, for not butchering my name. Oh, not butchering. Oh, that's good. So let's try it. Let's try it. Excellent. Okay, so back to my document camera. Let's get going. Oops, hang on. Just got to open the right Chrome tab. So let me just cancel that for a second. Sometimes the switching here just takes too long. There we go. All right, so question 16. We've got 3 points. So A is 1, 2, 3. B is -2, 3, 4. So these are points in 3-dimensional space, right? All right. So the question is, so you can see this is the way that I write my vectors. It's sort of a half arrow on the top. that's just there to save space. There's no real super important reason for doing it. This is page 38. Thank you, Pratikansh. Okay, so let's see what if these things are correct. So the first thing we'll do is we'll work out the vector from A to B and the vector from C to D, and we'll compare them. Okay, so how do we work out the vector from a point to another point? Does anybody have a formula or something that we can use to calculate the vector from A to B? Yeah, Lisa, it's right. So it's the position vector of B minus the position vector of A. Great. Okay. So we would write these as columns, and suddenly we have a magical position vector for each point. And you know, Niharika, thank you. And you know that to perform these operations, you just do it like component wise, right? So -2 minus 1 will give you -3. 3 minus 2 will give you 1. 4 minus 3 will give you 1. So that's the vector AB. Let's now do the vector CD. So OD is just that. Yep. And again, working component-wise, 4 minus -3, 7, -6 minus -4. That will be -2. And -9 minus 7 will be -16. Okay, so the big question now, are these vectors parallel? Yes or no? Who can tell me in the chat? Are they parallel? Joy says no. Lisa says no. Niharika says no. Aditi says no. Everybody says no. Okay. Well, how can we, so you're absolutely correct, Ricardo, Ryan. What you can do is you can compare the corresponding entries and see if there's a common multiple between them, right? So you can see here in the middle, there's 1. I can multiply that by -2 to get that. But if I multiply that by -2, I don't get that, okay? So we would say something like, since AB is not a scalar multiple of CD, our vectors are not parallel. Okay, so that's definitely the case where they're not parallel. Okay, now I'm going to jump to part C now because I want to do one where they actually are parallel. Okay, so this was not a particularly interesting example because they actually weren't parallel. So let me show you on the PDF where we are. Okay, so let's go down to here. Okay, so it turns out that some of these vectors are going to be parallel, and then this sort of forms an interesting question because for part A, obviously the answer is no, because A, B, and C, D aren't parallel, so there's no way they could be a parallelogram. Okay, but let's have a look at part C. Okay, so back to my document camera. Here we have 4 other points. Yep. Okay. Okay. So the same question applies here. Is the vector AB equal to CD? Okay, so let's see. To compute AB, you're going to get something like -10 as your first entry. So AB is going to be this position vector minus this position vector. And again, just like we did over here, we're going to work component-wise. So that's going to be -10, 10, and -10. Okay. And now let's work out CD. So that's going to be this position vector minus this position vector. Oh, okay. And so we're going to get -5, 5, and -5. All right, so the big question. Are these two vectors parallel? And Adnubhav has already said, well, there's something going on with the scalar multiple here. You can see AB is 2 times each entry of CD. Okay, so you're absolutely correct. And so AB and CD are parallel. Okay, so that's one where it did work, because if you multiply that by 2, you get that. If you multiply that by the same number, you get that. Multiply that by the same number, you get that. Okay, so that's a situation where they both worked out, right? But let's go to the second part of this question. Let me just share this quickly. This is the more interesting part, I think. Okay, so for part C, do any of these sets of 4 points form a parallelogram? So can we answer that question for these 4 points? Who can tell me on the chat? Do you think it forms a parallelogram or not? Do these 4 points form a parallelogram? Lisa says yes. Niharika says yes. Aditi says yes. What do people think? Let me know. Do the points in part C form a parallelogram? Ryan says yes. Joyce says yes. Everybody says yes. Okay. Well, let's go back. Oh, Alyssa says maybe not. Yeah, good question, Alyssa. Let's go back to our document camera and we'll see if we can answer this. So, what do you, for a parallelogram, what do you need, right? You need two pairs of opposite sides that are parallel. Now, as Alyssa said in the chat, the opposite sides are going to be equal. Okay, so what does this tell us? It tells us that those opposite sides cannot be equal in length because AB is twice the length of CD. Okay. Yeah, Caleb Wu, it's a good question. What happens if AD equals BC? Well, you'll get a pair of opposite sides that are parallel and equal in length, but what about these sides? Okay. So I don't think we need to discuss anything else. This tells us that these 4 points cannot be a parallelogram because, as Alyssa says, the opposite sides are parallel and they're equal in length. Okay? So since AB does not equal, so since these two lengths are unequal, we cannot have a parallelogram with our 4 points. Okay? It's just not possible because this tells you not only that, sure, these are A, B, and C, D are parallel, but AB is twice the length of CD. Okay? Yeah, Abdul Rahman, absolutely. A rectangle and a square are special forms of a parallelogram. So you're absolutely correct. It's a really good question. Okay? Yeah, really good question. Okay. So you'll see lots of questions in this week's tutorial about parallelograms. And some of them are just about showing things are parallel and the same length. Others are a little bit more conceptual. So they're trying to get you to think a bit more about what's going on here. So let me share the next question and we can talk about that. And if you have questions on the chat, just put them in the chat, right? Because I'm happy to listen to you and talk about whatever you want to talk about, right? Okay. So what about 17? Prove that these 4 points form a parallelogram. And which one of these sketches represents the parallelogram from part A? So the first part is more about proving something or showing something. And the second part is more about, well, what does the parallelogram look like? Like, what is the relationship between the different sides and the different points? So I thought we could do that one as well. Okay. So it's not a particularly difficult question, but part B is the interesting part as far as I'm concerned. Okay. All right. So let me go back to my document camera, and we can start this question. All right. So consider, please, the following points. Okay. And let's just, like what I'm going to do, I'm going to show, I'm going to calculate AB and CD and show that they're parallel and equal in length. And then I'll show that AD and BC are also parallel and equal in length. Okay. So AB is going to be the vector B minus the vector A. So what are we going to get? 4 minus 1, 3, 7 minus 2, 5, 8 minus 1, 7. CD is going to be something like that minus that, that minus that. So -5 and -7. Okay, so what do you notice about these two vectors immediately? They're parallel and they have the same length. Okay, so what this means is the lengths are also equal. Sweet. So they look like they're potentially the opposite sides, right? Or they are. So we know that one pair of opposite sides are parallel and they have the same length, right? So let's do that for the other pair. So instead of AB, let's go and do AD and BC. So AD is going to be D minus A. So you're going to get 2, -3, 4. Yep. And you're going to get BC. BC is going to be that minus that, which is 2. That minus that, which is going to be -3. And that minus that, which is going to be 4. Great, we're making progress. Yes. You can see that these are the same. Right? And if they're this, then of course the lengths have got to be equal. Nice. Okay, so we're just about to finish part A now. We know that these 4 points must form a parallelogram. Okay, and that's because the opposite sides are, you've got two pairs of opposite pairs that are parallel, both parallel, right? They have the same length. Okay, part B is the more interesting question though, in my opinion. Okay, so let's go back here to my PDF. And I'll go back to the document camera in a second. So which one of these is the correct setup? Is it I, or I? What do you think? And how might we work that out? Yeah, Alexander, I'm recording at the moment. So yeah, don't worry, there'll be a recording made available. Glad that you got a vaccine. That's really good. All right, so yeah, Doha, hello. Doha's claiming that AD equals BC. So AD equals BC. They've got to have the same direction, right? And from our working before, we know that AB equals negative CD. So definitely part I is the way to go. And Lisa, you're on the right track here with your comment. The opposite direction is where you go. So let me go back to my document camera, and I'll show you why this works and how we actually work it out. So if I was to draw, oh, that's not a very good. It's not a very good parallelogram, is it? Let me get something a bit better than that. Have I got one here? Yeah, this will do. Okay, much better. All right, so the setup there, A, D, C, B. Okay. So how did we come up with that? There's been some suggestions in the chat. So we know from over here, that's the relationship there, and that's the relationship there. So AD equals BC. So for two vectors to be equal, they need to be they need to have the same length and the same direction. All right, those two vectors have the same length and they're parallel. They both point in the same direction. For this one, that's the vector AB, and that's equal to negative CD. CD is going that way, right? From there to there. But for these things to be equal, we need to reverse it, okay? So this is the only situation from those three choices in our notes that will cover the two things here. Okay. Now that's an interesting question because it forces you to think about what these relationships actually mean as a picture. Okay. So I quite like it. I think it's cool. It's an interesting question. And especially the second part is really cool. I really like that. All right, folks, we're halfway through. If you have any questions, you can turn your microphone on. You can put something in the chat. Oh, Doha says 22. Let's have a look at 22. Can I do 22? Oh, it's a good question. Okay, Doha, I might save that for the advanced tutorial, but let's have a look at 21. Could we do 21? Because 21 and 22 are almost the same problem. Okay. Oh no, no. I'll do 22. 22 is easy. Well, it's not easy, but it's again conceptual. Okay. No, Doha, that's fine. By the way, Doha, are you in Doha now? I'm curious to know the relationship between your name and the city of Doha. So if there is one, let me know. Okay. You're probably in. If you're in Sydney, maybe the time's better, but let me know. Okay. All right. Consider three non-collinear points. Okay, and they have coordinate vectors. So these are like the position vectors, right, from the origin to the actual points. There are exactly 3 points so that you can form a parallelogram, calculate vector expressions for these 3 points. Maryland's excellent. Hope it's going all right over there. Pretty hot day today here in Sydney, everyone. Probably pretty hot in Maryland. Okay. All right. So let's draw a picture. And this is not a difficult question. It's just, again, more conceptual stuff. Okay. Oh, Abdul Rahman, India's super hot. Yeah, that's like boiling hot. Okay, so I'll just get started on 22, and then I can show you, like, you should get the idea. All right. So the best way is, Kuwait. Okay, Kuwait, maybe even hotter. So you've got 3 points. I'm just going to draw them like this. Okay, so this can be my point D, this can be my point E, and this can be my point F. Okay, and what I'll do is I'll put the origin in here. Okay, now I'm not worrying about axes. Sometimes when you draw the axes, it makes it look really horrible. So I don't care about any axes or anything like this. Okay, so I've kind of got a triangle here. Okay, so what the question is asking you to do is to find a fourth point such that this thing will be a parallelogram, and it's asking you to find the vector expression. So if I have a triangle here, what I would like to do is to add a point and make that into a parallelogram. Okay, so let's take that and go bloop over there. That can be one of my points. Okay, it's not the only point, but it's one of the points. Okay, so let's call that, I don't know, X. So now if you look at the thing, I've roughly got a parallelogram there. Okay, and what this question is asking you to do, if I can find my, oh yeah, is to go, okay, what is the position vector from there to there? Okay, so how can we get from there to there? Well, I know that. That's the position vector D. And I can get from there to there, which is the position vector E. Yeah. And I can get from there to there, right? This is just the position vector, the vector EF, which is OF. Okay. So who can tell me, how do I get from here to here in terms of D, E, and F? Can anyone tell me on the chat? Lisa. So Lisa says OE plus EF plus ED. Yep, you could do that. I think there's even a simpler way, Lisa. So Lisa's saying here to here, here to here, here to here, right? So you add them together and you come up with that. Is there even an easier way? Ricardo, OD plus DX, which is the same as that vector there. So Lisa, yeah, Lisa's done it in 3 steps, and then Ricardo and Stephen and Lisa have also gone in 2 steps. Okay, so that's the way I would do it. I would go from here to here, then from here to here, and when you add them together. So but hang on, there's a problem there, right? Yeah, well, I mean, I guess that's what, you don't know what this is. Okay, so to compute that one, it's just the same as this, right? So that, okay. So now all you need to do is put that in terms of F, E, D, etc. All right. Now, this is just one situation where the X is over here. If I draw these points again, let's say I'll go here and I'll go here. Okay. There are 2 other places where this X point could be here. I put it down here for this one, but you could have it here or you could have it here. So these are your 2 other options. Okay, so that could be a parallelogram or that could be a parallelogram. So that's one situation, but there are 2 other ones. Okay, so if you want to fully solve this question, you can consider these 2 extra cases and do them separately, like we did up here. Okay. All right. So all you want to do now is of lower case vectors. So you know your F, your E, your D, etc. Okay. Let's do another one. Are there any requests? If there's no requests, then I might just choose one. But let me know on the chat. But that's basically the idea. Draw a picture and consider the different cases. Okay, so let me go back to the PDF. So there's a few questions here. This one's a good one. Okay, so 24. I like that one because again, it's designed to help you for you to draw a picture and then to really work out what's going on in terms of addition and stuff and parallel vectors and whatnot. All right, so let's look at it. So these are position vectors of 2 points. We want to find the position vector of a third point, t, such that these vectors satisfy this equation. All right, so for this one, it's not a difficult question, but some students, they're not quite sure where to start with this problem. So the best advice that I can give is to actually draw a picture, okay? So it's not hard once you know how to do it, of course, okay? So let me go back to my document camera. So we've got 2 points, A and B. All right, and we join those 2 points to form the vector from A to B. Now, what we want to do is find the coordinates or the position vector for this point such that the vector AT is twice the vector TB. So this vector and this vector satisfy this relationship. Okay, it's not a super good drawing, but this distance here is twice this distance. Okay. So how do we do it? Well, one of the you can do this problem a few different ways, but one helpful way is to draw in the origin, and what you want is that vector, because if you know OT, you know the position of the point T. Okay, so how can you get OT? Well, OT is just OA plus AT. All right, so given this, we want OT. So by the addition law, OT is OA plus AT. Now, we know a relationship here. Okay. So let's see if we can use that as a strategy. Okay, we know what A is. Okay, and AT is twice that. Okay, so basically T breaks down the vector AB into 2/3. Okay, so AT is 2/3 of the vector AB, because you've got that section and that section. This section is twice as long as that section. Okay, so that's where this comes from. Okay, so let's use that and we can work this out. Okay, so make sure you understand where this came from, right? Because if I can just put it here, AB equals AT plus TB. Not everybody understands maybe where this came from. So yep. So TB is that. So if we just rearrange that, oops, sorry. Okay. So if some of you are thinking, oh, where did this come from? Well, we use it from that and the fact that AB is AT plus TB. Great. So let's do it. So OA, what are our points? Oh yeah, okay. So OA is just this. AT is that. So the vector from there to there is just that. And so we can simplify this now. So that's going to be 1/3 A plus 2/3 B. All right. And I can see people on the chat getting into it. Yeah, so Abdul Rahman, close, but not exactly. Because remember, the vector AB is the position vector of B minus the position vector of A. Okay, so Ricardo's got the correct answer. OT, yeah, so this is your OT. But again, you can see it really helped to draw a picture and then what kind of ratios are going on here. Use the addition property and simplify. That's essentially what we did. Okay. Shall we do a calculus one? People were asking about the pinching theorem, right? So I might just switch over and do a pinching theorem one, just because I haven't done it in lectures yet, in the calculus lectures, but I wanted just to show it to you as well, okay? So let me share this with you. And you'll see it in lectures on Thursday, but let me just share it with you anyway, okay? So should come up, yeah. Use the pinching theorem to find the following limits, okay? So we've kind of discussed some of these limits in week one, but in a very informal way, okay? We're not really proving anything. For the first one, you know that x gets very large, and so it drags sine x down towards 0, okay? But what happens if they're asking us to use a specific method for the pinching theorem? Okay, so the idea is just to use basic inequalities. Okay, so let me show you how to do that. I'll share my screen again, and I'll see if I can I'll give you some idea of what it's like. Okay, so this is what we're asked to compute. Okay, so we have some idea that the answer is going to be 0, but let's actually use the inequalities. Jovanka, it's page 47 in the calculus course pack. Okay, all right, so let's consider sine x. Okay, now this pinching theorem, it relies on inequalities, okay? So when you're trying to solve this using the pinching theorem, you basically want to start with a basic inequality or a basic pair of inequalities, okay? And so what I can do now is multiply both sides to get something like my original function. So I'm going to multiply both sides by 1 on x, and I'm going to assume that x is positive. Just if x is positive, then I don't need to worry about, well, do the signs flip or anything. I can just keep them the same. All right, so believe it or not, that is enough to get you going with the pinching theorem. So you can say by the pinching theorem, we take the limit of the left-hand side, we take the limit of the right-hand side, and if they're equal, it forces the thing in the middle to be the joint value. Okay, so okay, so who can tell me what is the limit of the left-hand side as x goes to positive infinity? What am I going to get here? And here also 0, right? Yeah, thanks guys. So this is going to go to 0. This is going to go to 0. So I've got a limit in the middle that's bigger than 0 and less than 0. Okay, the only way that can happen is if the middle thing is 0. Okay, theorem. Okay, so if you've got something that's greater than or equal to 0 and less than or equal to 0, it's got to be 0. Okay. So let me bring up GeoGebra here because it's an interesting picture when you see what's going on. So I'll just, while you're copying that down, I'll just put some stuff into GeoGebra. Okay. Okay, so let me share this with you. All right. You should be able to see that now. So if I zoom out, this is sine x on x, right? And it looks like it goes to 0. But let's compare it with a couple of other functions, 1 on x and -1 on x, okay? So you can see what's happening. The gray function is being squeezed between the red function and the green function. And both of those functions go to 0. So it squishes the wobbly function to 0, okay? Now, this theorem has a few different names, okay? This theorem has a few different names. It's called the sandwich theorem, the pinching theorem, and the squeeze theorem. There's another name for it called two police officers and a drunk. Okay, and the idea is you've got a drunk person who's moving around, and the two officers take them to the cell, right? And it doesn't matter what the drunk person does, if the officers are above and below and they both go to the cell, they take the drunk person to the cell as well. Okay, so yeah, two policemen and a drunk, or two police officers and a drunk. That's another way of describing the theorem, right? So if I show that again, here's the grey crazy person. The red person's a police officer, the green person's a police officer, and both of those officers go to the cell. It means the person in between them has to also go to the cell. Okay? Yeah. Prison break. Love it. Okay, everybody. I think that's enough questions for today. If anybody wants to have a quick chat, let me know. Feel free to turn on microphones at any time and discuss anything with me. Don't forget your Mobius assignment for week 1 is due in 6 minutes. Thank you, Alan. Thank you for coming. So, yeah, I'm glad that you're enjoying. If you have any musical requests for next week, let me know. Yoshi would like some musical requests too. So yeah, let me know. Let me know. And just enjoy the day. It's week 2. I can't believe it's week 2 already. Blues, Jovanka. Yes, we can get blues. So at the moment, the requests are for jazz and for blues. If you have any particular jazz songs or blues songs, I'll definitely play them. Okay. Oh, Sinatra. Wow. All right. Sinatra. Okay, sounds great. The Weekend, Carl. Keep them coming, everyone. Ooh, Donda. I'm just making notes. Drake. Donda. All right.